Are you still using a flat percentage increase for future rainfall in your flood models? That method is now outdated. The latest Australian Rainfall and Runoff Guidelines version 4.2 have changed how we project climate impacts. So, how do you apply these new duration-specific factors to rainfall and loss inputs without drowning in data? In this video, I will walk you through ARR 4.2 step by step and show you exactly how to calculate and apply the new climate change factors in Excel. Let's dive into it. Hi, welcome to Water Data Hub. I'm Amin Tully, and if you are passionate about water, climate, and engineering solutions, this is the channel for you. Well, let's start the step-by-step process for calculating the climate factors based on the new ARR guideline. Before I proceed to the calculation part, I want to also highlight the major changes that have happened in the new guideline compared to the old one. As you may know, basically the climate change informations are available in Book 1, Chapter 6 as before, and the new guidelines have a more robust and nuanced assessment of future climate. One major change that has happened compared to the old guidelines is a shift from the RCP concept or representative concentration pathways to the shared socioeconomic pathways, which is a totally different philosophy for calculating the climate change or let's say in general climate projections. And this is based on the latest IPCC report, the 6th assessment report, AR6, which is adopted in this guideline as well. The major change that we have in climate factor calculations is related to the rainfall projections that in the new guidelines we have a duration-specific approach compared to the previous one, which was suggesting a kind of constant climate factor for different durations. So basically it was independent from duration. And another parameter that also has been added is the calculation of climate factors for initial and continuing rainfall losses, which wasn't available in the old guidelines. So what is the methodology? It's basically very simple. Imagine you have a baseline value for your hydrological parameter, and then you will get a multiplier, which we call it climate factors. And by multiplying these two, you will get your projected hydrological parameter. So in general, this hydrological parameter for us here can be rainfall, like depth or intensity, and also can be rainfall losses as initial or continuing loss. So when it comes to the climate factors, for the rainfall case, it will be duration specific, as I mentioned earlier. So means for each specific duration, you will get a dedicated climate factor. But when it is about the rainfall initial and continuing losses, it will be independent of duration. The formula that we use here for calculating the climate factor is coming from equation 1.6.1 of the guidelines. And it's a very simple formula to play with. The parameters of this formula are listed here. IP is the projected hydrological value, and as I said earlier, can be rainfall depth, intensity, initial loss, or continuing losses. And then we have I as the baseline value of that parameter, and then two climate parameters that we have here. Alpha is the rate of change, and delta T, which is the global temperature change. As you may know, when we talk about climate change, generally we are talking about an increase in global temperature. And now we want to show how this change can affect, for example, the rainfall intensity or rainfall depth or the losses. So our major task in this process is basically finding the suitable alpha and delta T and then putting it into the equation and get the projected value for your desired parameter. So let's go through this step-by-step example. In order to have something to start with, I have decided to choose a site located at Southeast Melbourne. I'm using ARR Data Hub to get access to the required data, which I mean, basically what I mean here is basically rainfall, losses and other required parameters that I want to look into their projection. My projection year is going to be 2100, and I'm going for the worst case scenario of climate change, which is SSP 5. So when you go to the ARR Data Hub, you can basically navigate on the map and find your desired site, or simply enter the coordinates of that if you have it. And then from there, you will get access to a big list of information available for that specific site. One of them is a link to the BOM website that you can download the IFD, the intensity, frequency, duration, rainfall data. And that one can come as a chart or table. Here we prefer to play with table because at the end we are going to have Excel calculation for that. That's why I think table definitely is going to be more useful. One point that I want to highlight is that on the same page, when you find your location on the ARR Data Hub, you can find also your initial and continuing loss recommended for that site. As you can see, for example, in this case, I have 27 mm for initial loss and 4.4 mm per hour for the continuing loss. Another point to highlight is that you have the option to download the IFD table as rainfall depth comes in mm, or rainfall intensity coming in mm per hour. Most of the hydrological models, including RORB, which is common in Australia, needs the data in mm. That's why I also show the example here as rainfall depth. Another point to highlight is that in this example, I want to play with 1% annual exceedance probability, or AEP. And of course, you can play with others, but here is the example that I'm going to cover because that's one of the common design criteria for the drainage assets. So step 2, after having your hydrological data ready, you need to get access to the suitable parameters of that equation that we discussed. The first and perhaps the most important one is the global temperature change, or delta T. And for that one, we have a table in the guideline 1.6.2. And this table basically has two types of information for you. Number one is the climate change scenario. So you need to decide which scenario is the one that you want to pick. And then the other one is that what projection window is your desired one. Are you going to look into the near term or medium term or long term? In this specific example, I'm looking into SSP5, as I mentioned earlier, and I'm going for year 2100, which falls in the long-term projection, basically. So as you can see, the recommended delta T for this choices that I have basically is going to be 4.1. But I want to highlight one important point, that this number 4.1 belongs to the center of that projection window, which means center of 2081 to 2100, which is the year 2090. So if I'm interested in 2100, this 4.1 is not the number that I need to pick. So what should I do? For that one, I refer to this diagram. This is basically a diagram that shows the global temperature change for different SSP scenarios. As you can see, it starts from the blue color one, SSP1, all the way go to the red one on top, which is SSP5. So the last line is the one that I'm interested in. That's actually the median line for the range of SSP5 values that we have. So what should I do? 2090 gives me 4.1. So now I look into 2100, that touches the line somewhere here, and that gives me 4.5. So that's the delta T that I'm going to adopt for my calculations. So 4.5 degree centigrade increase in global temperature. Now coming to step 3, it's the time to select the rate of change, or alpha, for our calculation. So here, what I'm going to do is referring to table 1.6.1, and this is the place that for the first time you will see the story of duration specific point that I mentioned earlier. So alpha is the one that basically brings in the impact of duration into the climate projection. So in this table, as you can see, we have 3 zones. If your rainfall duration is smaller or equal than 1 hour, the rate of change will be 15%. And if your rainfall duration is equal or larger than 24 hours, you get 8%. And of course, if the rainfall duration is something in between, we are falling in an interpolation zone. And of course, the alpha value should be something between 15 and 8. And for that one, a dedicated table 1.6.5 will help us to get access to the interpolated alpha value. So you don't need to do anything manually. The numbers are provided, and I will show you later when I get to that point. So this is the 2 zones as I mentioned earlier, and interpolation zones for anything in between. So let's have some examples. So our summary, 15% for short duration, 8% for long durations, and interpolation for anything in between. Let's have an example of 45-minute duration on the AEP 1%. I refer to my IFD table for 1% and 45 minutes. I get 41.5 mm depth of rain. I bring it here and then I say that, okay, it's a short duration one. Alpha will be 15%, our delta T 4.5. I apply it into the equation. Very simple. You get 77.8. So 15 sits here divided by 100. 4.5 is the power of the bracket. So that means my rainfall depth has increased by 87%, which is significant. So now let's move to another example. So I purposely go to something with a longer duration. Now I have 48 hours on the AEP 1%. And for that one, I go to IFD table. I get the number of 156 as the rainfall depth for this selected duration. I bring it back here, 156, same scenario of SSP5 and year of 2100. My alpha this round will be 8%. Same delta T, I applied in the same equation. So this round 8 will be divided by 100. And this is my baseline value. And I get 220.6 mm. And this is 41% increase. This is almost half of what we had for the short duration. So that's the message here for us, that based on the new guidelines, the shorter durations events are affected significantly compared to the longer duration one. So what about the interpolation zone? Let's have an example there. This is the table that I promised to show you, table 1.6.5. And as you can see, for typical rainfall durations that we generally play with between 1 hour and 24 hours, the alpha values are provided. So I just simply pick whatever I want. So just for the sake of example, imagine I go for 6 hours and I will get the alpha of 10.2. So I refer to my IFD for the 6 hours under 1% AEP. My rainfall depth will be 73.1. And I bring it here. Again, same scenario of the climate change. My alpha 10.2 and delta T same. So if I apply that into my equation, this time 10.2 will be divided by 100. Same power of 4.5. And the answer is 113.2 mm. And that's 55% increase. If you remember, for short duration we got 87, for long duration we got 41, and now for the interpolated one we get 55, which is obvious. It should be something in between of those two numbers. Okay, step 4. Now it's the time to look into the rainfall losses projections. For that one, the good point is delta T is not going to change. I'm using the same delta T. The only thing that needs to be found from the guideline is the alpha, or the rate of change. And for that one, we have a table, 1.6.3. So this table has a dedicated column for initial loss and another one for the continuing loss. What about the rows? Actually, the losses are depending on the location. So in our case, we are in Melbourne, and Melbourne falls in Southern Slopes mainland. And for that one, the numbers that I need to pick from this table is 3.9 for initial loss and 8.5 for the continuing loss. And I bring it into my next level calculation. Interestingly, it's not going to be different in the formula, same formula. So I have the 3.9 and 8.5 ready. Delta T, as I mentioned earlier, similar. So we applied into our formula. So for initial loss, 3.9 divided by 100. This was my initial value, if you remember. And I get 19% increase. If I apply the same process for the continuing loss, this round I have 8.5 divided by 100, and my continuing loss value was 4.4 from the Data Hub, and I get 44% increase. So the message that I want to pass here is that if we look into the projections for the losses, continuing loss is going to increase more compared to the initial losses. And another important point was the fact that the changes in the initial and continuing loss are independent of the duration of the rainfall. So they are not related to the duration. So now let's bring this calculation into Excel and see how we can basically do the same process for the whole range of rainfall durations, and even if you like, for different SSPs. So when you go to BOM website and download the IFD rainfall information, that comes in a CSV file. I mean, of course, there are other options like a graph or PDF files, but we prefer the CSV or the Excel file. So this is how it looked like. So you can see that for different AEPs, starting from 63.2, which is a very frequent frequency of the rainfall events, all the way to very rare one, which is 1 in 2,000. In this specific example, I'm just playing with 63.2 all the way to 1%, which is the range that generally we use for designing the drainage assets. So I have done the copy pasting for you to just save time. So I've brought the values here, and I have given a color to the zone that is going to be interpolated later. So just to understand that when we reach to this point, the values for alpha are going to be interpolated. So how should we start the calculation? I start with the alpha value, which is the rate of change. And just to recall what we had for the rate of change, we are using this table. For the short duration, 15%, for the long duration, 8%, and for anything in between, interpolation. So I come back here. For the short duration, I enter 15, and I can drag it for all the rainfall values up to 1 hour. And then when it comes to long duration, I have 8%, and I can drag it all the way down to the end of the row, that which is 168 hour. So what about the interpolation? I need to fill it, and if you remember, we had a table for that. So the table is here. I just bring it here so we can see what we are doing. I paste it here, and I enter the values. So for the 1.5 hour, 13.7, after that 12.8, then 11.8, 10.8, 10.2, 9.5, 9, and finally 8.4. So we have all the values that we need. I remove this table, I don't need it anymore. So now we go for the delta T calculation. So basically the delta T comes from the table that we had. And if you remember, I had an issue. The value in the table was related to year 2090. I'm talking about this one, this table. And I needed to go through the diagram to find it for 2100. So by right, I need to repeat the same process for SSP3, SSP2, and SSP1, but I'm not going to do that. I'm going to show you a shortcut. And that shortcut is the fact that this information that I'm looking for are available as part of the data shown on the Data Hub. So I'm going to show you how you can see and bring it into your Excel spreadsheet. So the data hub for my specific site looks like this. The location is shown on the map. If you scroll down all the way down, you will get to a table. I zoom in a bit. A table that says temperature change degrees relative to 1961-1990 baseline. And as you can see, this table shows the values for different years, projection years, and for SSP1 all the way to SSP5. And what I'm after is basically this part, the 2100. So the numbers 4.5, 3.6, 2.5, and 1.4, that last time I needed to find them from the graph, I can simply adopt it from here. So that's what I bring to the Excel and continue the calculation. Well, by having these 4 numbers from the data hub as I showed, so what I need to do is just simply drag them all the way down to the last row of my table, because these numbers are not going to be duration specific. So whatever delta T you find, it is applicable to all durations. So that's why I just drag it and repeat it for every row of this table, which means for different durations. So now we are ready to calculate the multipliers, or what I showed in my slides as climate factor, CF. So that follows the equation that we had. So let me bring the equation. So this is the equation that I'm using. Just I put it somewhere here so you can see it. So what I'm going to calculate is basically the value inside the bracket. That's the multiplier. So for SSP1, that will be, I open a bracket, 1 plus my alpha, which is 15. Divided by 100, and then I give it a power of my delta T. Before I proceed, what I'm going to do is that I'm adding a $sign here in order to fixing the alpha value, because that is not going to change for different SSPs. And I drag it like this. And after doing that, what I'm going to do is just simply dragging everything down all the way to the bottom of my table. So here I generate everything. So all the multipliers are generated, including for the interpolation zones, because what I did was just simply adopting the alpha and the delta T and then put it in the formula and get the numbers. So we are done here. So the next stage is calculating the rainfall projections basically. So this part is relatively easy. I have a multiplier, I have a baseline rainfall value. I just need to multiply them together. So it starts very simple here by saying it will be equal to my baseline rainfall, which is this one. And then I multiply that to the multiplier under SSP that you have in mind. For example, in this case, I'm just showing it for SSP5. So I multiply it to SSP5 multiplier. So that's what I get. Again, like last time, in order to just fix the multiplier, I'm going to add a $sign here behind U. And by this, I'm actually fixing it. So now I can drag. And with these, I can simply generate all the rainfall projections for the first duration. And then I drag it all the way down to just get the values. So here, as you can see, very quickly, I can generate the SSP5 for 2100 values of rainfall depth. One more thing that I would like to show is a comparison of this projected value, just in order to understand how big the rainfall has become under this projection. I want to compare it with the baseline very rare events. So what I'm going to do is basically copy and pasting the 1% value here and compare it with the very rare scenarios on the baseline climate scenario. So that's what I'm going to do, is just copy pasting. So let me copy this column which is the 1% projected, and I go back to the original table that I had and I paste it here. So I just paste the values. Perhaps I also would like to look into 2 decimal places only. And this is the SSP5 1% 2100. So that's the projection that we have. So how does it look like? If you compare, you can see that basically for the short duration events, the values that I have for SSP5, I think I've made a typo here. This is SSP5. Yep. For SSP5, the values are very close to 1 in 2000. If you compare, they're relatively close to each other, like 22 versus 21, 27 versus 25. The more you go down for larger duration, you see that the gap between these two values get larger and larger, basically. And when we reach to somewhere, for example, maybe here, which is around 4.5 hour rain, for example, you can see that now I'm closer to this column, which is 1 in 1000. So basically my projected value, when it is in the short duration, it is somehow equivalent to 1 in 2000 event under the baseline condition. And when I go for the longer duration one, it gets closer to 1 in 1000, which is a relatively smaller event if I want to compare it to the 1 in 2000. So you can see how big the changes are by under the worst case scenario and under the new guidelines. The other point that I want to highlight is about the climate factors that are provided in ARR Data Hub. Let me bring you back to the portal of ARR Data Hub. If you remember last time, I showed you that the temperature changes, delta T, are provided here. So it's good to know that after the release of the new guidelines, the Data Hub also was updated to provide some information for this change. So I just showed you this one, but if you scroll up, you will see that there are more tables related to the climate change. For example, here you see for the initial and continuing losses, basically the climate factors, those multipliers that we just calculated in Excel, are provided for different years and also different SSPs. And if you scroll up more, you will see that for rainfall depth as well. But for rainfall depth, since it is duration specific, you see that there are tables dedicated for each scenario. For example, SSP5 has its own table, then SSP3, then 2, and then 1. So these are exactly the same multipliers that we just generated in Excel. So question remains that which one is easier? Honestly, depends on you. As I showed you, the process in Excel will be very easy. Once you have those multipliers, you can easily generate all these SSP scenarios in few seconds. Alternatively, you can just bring these multipliers and go back again to Excel and do the same process. So it's honestly up to you. I would say the amount of time that you need to spend to generate the projected rainfalls before fitting it into your hydrological model will be relatively similar. It's up to you. So I leave it to your judgment which one is more comfortable for you to use. Okay, with this, we have gone through the step-by-step process of calculating the climate factors. And if I come back here, you are basically ready now to generate the projected rainfall depth and fit it into your hydrological model. For example, if you're playing with the RORP, which is one of the common hydrological model in Australia, you need to provide rainfall depth, the projected values, and fit it into your model and run your model based on this projected rainfall to get your projected runoff out of that. And of course, you need to repeat it for different scenarios. That's why I think what you generate here in this table is going to be the food of multiple runs in RORP, for example. So here if you want to check, for example, scenario SSP3 or SSP5, you need to have like separate runs for that. And each time you need to provide the right projected rainfall value into that. The next point that I want to highlight is about the scenario adoption. Which one should we adopt? Honestly speaking, the guideline doesn't prescribe anything. So it is basically related to the risk appetite of the projects. Currently in the industry, some people advise that perhaps it is good to go for SSP3 and design based on that, and then run some sensitivity checks for SSP5, which is the worst case scenario. But I would say that this is still a subject of discussions among experts in the industry. And I still believe that risk is one of the most important factors that tell us what climate change scenario needs to be adopted for the project. If you are interested to know more about climate change, the reasons behind it, the science of it, and also a better understanding of the SSPs, I have a dedicated video on that, and I will provide the link to that at the end of this video. If this video was helpful, please give it a thumbs up and subscribe for more practical engineering tutorials. Got any questions on ARR 4.2? Please drop them in the comments and I will do my best to answer. Thanks for watching. See you in the next one.